Okay, so let's talk about what HiHAT is. So essentially, there are 4 phases to this, and this can be a little bit confusing, so try to keep this in mind in what it is that we talk about as we move forward. First, it's a community-wide requirements gathering effort. We want to make sure that we don't build something useless. Otherwise, this is a huge waste of time. So we want to go and make sure that we've understood people's usage models, their requirements, and are building something that people need. We also need to know what the priorities are with which we should build those things out. So that's the way in which we want to make this community-driven. We also want to have an effort to architect the user and common layer, and we'll define what those are, and come up with an API and an implementation for those, and then have a way to plug in beneath that some implementations beneath those that can be vendor maintained and user supplemented. So got a little build here. So HiHAT, this is sort of where the APIs and initial implementation will be at this layer. And so we'll start with this and we'll sort of expand that. And the applications are up here. The applications are not our initial customers. Our clients are essentially low-level runtimes and language runtimes and high-level runtimes built on top of those. So we'll go through examples of all of these 3 boxes and 4 boxes. And there's more material on the backup about sort of some of the things that are going on here. It's then the responsibility for each of the different vendors and those others who want to play and sort of show up the vendors to say, what's the best mapping from this stuff down to the actual hardware, or down to something that's actually going to do these low-level activities. And so we have a number of people that we'll talk about. Sort of this is sort of where the implementation layer comes in. So talking about clients, the first and primary clients are those who are already existing. You already have something. It already works on one or more platforms. And so then you have to ask, for example, the C++ runtimes out there, the Calcos runtimes out there. Carter's going to tell us that, they had some great presentations the last couple of days. And you see, if you look at this, that you can have a task graph, and you can send it to one target, or you can send it to another target, but in its current implementation, you can't take one task graph and map it across 2 different targets. And you can comment on this later, but essentially, we're trying to provide the infrastructure that makes things enough more retargetable that you can do and hit those multiple targets. So the other thing is that there are those that are being designed. So Antonino is going to talk about the Hive and Kaggle effort. So folks that are sort of coming on the scene like, hey, we got money, we got a project, we got to build something. How are we going to build it? We have some ideas of what we want to do. We have some different alternatives of how we can architect it, how we want to layer it. Is HiHAT going to be there soon enough for me? I don't know. But in case they do, I may want to architect what it is that I'm doing so that it's compatible and I can layer on top of that. So, and the part of our gathering the community requirements, that should also serve the function of being able to inform those who already have something or that are looking to do something. It's like, hey, here are the hot things. Here are the things that you may not have considered that you may want to do because of the gathering of these different requirements that we have. And another here is essentially HiHAT is providing this target neutral interface. So it's essentially the boundary between all the things that may be target informed. They may know about the parameters of the target, but they have code that is independent. The heuristics that they can use can be independent and not particularly target specific. And HiHAT provides that target spanning interfaces, and then there are implementation specific things that plug in underneath that. And we'll sort of unravel what that looks like. So the key thing is that the clients, especially those that already have something, can look at this and say, what do I most need? Where do I have needs? Like, I am about to start another implementation. And man, it was a lot of work last time I did that implementation. Or I did it for this implementation, I already have it, but this vendor is coming out with some new features. How am I going to use that, right? I have something up, I had some grad students do it, and they had enough to get a paper, but man, it's really not robust. If I could take whatever it is that I have, I could throw that away and replace it with something else underneath. I just want to make this easy. So those are some things you want to do. And the notion here is that you want to make this so that it's incrementally adopted, so that you can use just portions and slices of what you want rather than having to go whole hog and say, rewrite everything to use it, and build up from there. And so we do not have a near-term goal of providing sort of user-facing runtime. It's possible that we'll make that incrementally easier to get. So in the longer term, so this is not where we're starting. So we talked about this user and common layer just a minute ago. Now we want to move on to looking at what we want to do for an open source project. So imagine that there are, say, 4 different organizations, and they have needs in common, and each one says, well, I need a scheduler, I need a cost model, I need a visualization thing, I need a whatever. They all need something, and they don't have enough resources. None of us has enough resources, right? I don't have resources to do all that. But if enough of us can get together and agree on what we need and write a stack for the kinds of key modules, key building blocks we need, and then we can start sharing those, then hey, we're doing something, right? So we're finding inside NVIDIA that we already have several projects. Dilip's here will talk about one of the things that we have for the deep learning space. We have several others of things that we're doing, and those, not surprisingly, sort of grew up in an ad hoc fashion, where we have several different runtimes that are not sharing infrastructure. They're all starting from scratch. But if we can find and test and robustify those common building blocks, like, hey, your scheduler is better than mine, right? But I can now make it better. Your cost model, you had some subtle things in there, right? And if we share that and check it in and work on those, then we can move forward together. So the HiHAT interfaces are going to define the types of the machine model and define an architecture that clients that build onto it can conform to. And then we want to do this as an open source project. And here's I mentioned a number of examples that we put on this. And essentially, this is the key thing. If we're going to do a robust product, we want to be able to test the daylights out of this. And the more people that are banging on it and filing bugs against it and fixing it and checking it out, the better product will do. And so people who use it can chip back in. So then there's an implementation layer, and this essentially is the part that's beneath this. So what the HiHAT layers do is essentially just a simple dispatch to something that's target specific. And then there needs to be some glue code down from the hardware platform to that may be specific to each vendor. So there are a lot of things for a CPU may be pretty common between an Intel or a Power or an ARM CPU because it's a CPU. It's probably using a lot of LMC, using a lot of Unix, right? Or whatever. It's not a whole lot different. You're doing to an FPGA or a GPU or whatever may be substantively different. So this is basically the functionality that's behind these APIs. And again, the vendors have the strongest incentive to do this, but others may offer alternative and improvements in implementations. And we'll talk also, we have 2 presentations here today on threading. So for example, with Q-threads and Argobots, we also have some stuff for UCX and so on that Paolo's going to do from online. So let's get to a picture. So this is a little bit of a busy picture. Essentially, think of this as layers. So the applications and the frameworks, compilers, runtimes, and libraries are up at the top. Down at the bottom are each of these respective different hardware types. And what's in between, this is essentially the user layer and the thin common layer. These are the things that are the HiHAT APIs. And then we have implementations to meet those. And these are just pretty dumb. They just do this much. They have a way of saying, here's the work that I want to do for this API that's common across all these different targets, and I'll pass in an extra argument which identifies the kind of target that I'm doing this for, and they will correctly select the appropriate thing that it wants to dispatch to. And they also have targets for, I want to have a different layout for one target than I do for the other. So being able to take the work that may be target specific, encapsulate it into a task, and have the stuff that happens outside of the task be the thing that manages invocation, data movement, these other different kinds of things in the target specific way, and be able to deal with different layouts, right? So I can say, great, I actually have a couple implementations, and if the data is in the right data layout, I can this one to be a whole lot faster. And we'll talk later about how you can essentially say, well, but I got slack time. I can just make the conversion of the data relay out yet another action that I work into my dependent system, and I can make it data ready as soon as the data is arrived, in the right format. Right? And then I can pick a faster version of this. So essentially, these tan boxes apply across all these different targets and do things like these two layers. And I'll talk a little bit about that. See, these are the building blocks that we have that are built on top of this, and those are shared, distributed utilities, and that would accelerate the coding and share technology, increase the robustness. So, and again, trying to do things in a way that are future-proof. So, if you think about this again, how many boats can you float, and how can you make this work? We're trying from the bottom up so that you can have people wearing very many hats, if you will, on top of this. That's the notion. So, any questions here before we go on? All right. Value. Why would we want to do this? Why would anybody want to try this? So, how many people have done something where they tried to write code that they had to port from one target? And oftentimes there are surprises. You think that it should be the same, and you end up having to become kind of an expert. My own experience is that you have to become an expert at a compiler. You have to become an expert in the language. You have to be an expert in the microarchitecture, and then all the other utilities and stuff that run on top of it. And it's a huge learning curve. Some of us really like doing that, but a lot of us don't have the time to do all that. So essentially, if you have a modular design that can achieve the separation of concerns, then the stuff that's above this user common layer can be target agnostic heuristics, even though they're informed by this. So if you want to do a schedule, you want to know for this particular target, how long does this task take on that implementation, that target versus this target? How long does it take to move data if it's coming from here, right? And when you're making a scheduling decision, you can look at where is it going to finish first, right? This next thing that I want to schedule. Given the cost of moving the data, the cost of doing the execution, and the availability currently on that side resource, or how much memory is there. So making it retargetable across these vendors and implementations and generations, and so you don't have to chase those changes and improvements. You essentially worry about changes to this API and make sure that you're providing enough information that you're using the right features and the right target. I think that's what. So going after performance and robustness is key. Okay, so you should be asking, so state aware, what's going on with this? Where are we? Are you actually going to do anything? Are you just going to stand up and talk about this? So we've been trying to make some progress in this. So remember, our 4 phases have to do with gathering, architecting, implementing, and integrating. So we've been gathering for a while, and we've been capturing a fair bit of that information on the wiki. We encourage you all to go visit the wiki and make at least one post yourself. And have the notion of, do the best you can in 20 minutes. If you have an idea, scribble something down and let somebody else go edit it after you to add more stuff. We're trying to architect things, and we'll kind of roll out today some of the design principles that we have. So we don't have an API document, but we've made significant progress in what it is that we're doing and why it is that we're doing it and how the approach we're going to take. So we'll do that in the latter part today. Our plan on implementation is this summer to do a really simple proof of concept on top of this. And we're anticipating a partial implementation of this by the end of the year. That's at the HiHAT layers and starting to go down to some of the deployments. And then from there, we want to sort of move forward. And this is sort of a rough notion of a timeline here. We started this back last fall of 2016, and we're sort of moving this through. So the community, we're looking to get input and then review what we have. We're sort of doing some of that today, and getting some of the community feedback and sort of continue to integrate this into broader, more complete solutions. So again, any questions? This is an aggressive goal, but I think it's achievable. It's achievable if we continue to work together and to accelerate from where we are. So momentum we have. We have some monthly meetings to talk about this, so if you're not signed up for those, please go to the website and we'll get you into that. We have some of these active discussions. We're meeting several hours a week to sort of work through some of these issues. We have some existing proofs and past learning that have been really helpful in enlightening us. Great discussions, for example, with the guys from CodePlay who've done SYCL and a bunch of the C++ runtime stuff. And Paul Shamus, who's done a lot of the UCX work, those different areas of people that have sort of gone and built this stuff. And of course, we've had Sean, who did Realm, been very involved in this knowledge too. We're starting to see some funding from this, and people are interested in sharing some work from this. We have a number of different efforts that are going on, like those in Switzerland with PAST and other kinds of things. And just a plug, we have another, the iWalker workshop has a section on the distributed and heterogeneous programming that's May 16th. So that's coming up. And we'll be talking about this too at the performance portability workshop. All right, so I'm going to just go to the next level of detail here. What is it that you would want out of a system like this? So basically, there are actions and services. We'll talk a little bit about actions later here, but an action is basically, I want to get something done. And like I got the fire off this computation, got some target-specific code, and I want to be able to select the right one based on what the target is, the implementation, and the layout. An example is that I would invoke a task named foo on target X. And I want to be able to deal with different data layouts, all kinds of different places I could move data, whether it's from a CPU to an accelerator, whether it's across the network, whether it's through PCIe, whether it's all inside the CPU, whatever that would be. And then there's coordination and control, the synchronization and moving things back and forth, dealing with enforcing dependencies, queues, and the like. And then something that happens up at a higher layer is scheduling. Basically doing the binding and ordering and making the trade-offs across these multiple targets. So again, I want to just emphasize the goal of what we're doing is to be able to have a framework which can deal with a heterogeneous platform, whether it's all the platform is a given type, but I have to deal with multiple platforms, or a given platform has multiple resources inside the same. So this is sort of the scope of the functionality that HiHAT APIs are looking to provide. And so these are the different things that people are going to sort of talk to as we go forward. And we're still trying to figure out what debugging means, but lots of people think that's really important, and we know that it's never worked in the past. So that's an area that we think is key. A key notion that we have as a design consideration for this is that being able to serve both, make it easy to get started so that I don't have to completely specify everything that happens, but also be able to have transparency as to what's actually going on, which is why tracing is really important, and control. So for example, if I need to be able to have reproducible floating point data, I need to make sure that it runs the same way every time. I may be willing to sacrifice some performance for that, but I got to make sure that. Okay. So these are the key things that we'll come back and refer to. So now I'm gonna ask Max to come up. And do you want to use this or do you want to use this? So yeah, I'll just let you talk.
Thanks. So CJ let me have a few minutes to kind of talk about applications in the HiHAT effort. Like you said, this isn't a research project. So, the end goal of this isn't an SC 2018 paper. The end goal of this is every, Gordon Bell submission finalist in 2019 has to run on this, because if they don't, they can't achieve, whatever their goal performance is. And to kind of reinforce that and emphasize that, one of the kind of early efforts in the HiHAT project has been to gather requirements, the kind of parallel patterns, synchronization features that parallel runtimes need to support their application. And this is just a small subset of the kind of applications that people have been posting on the HiHAT wiki, and what we've been using to kind of drive the design of the user and the common layer that CJ mentioned. I can go through any of these in detail. Is anyone particularly interested? I was just going to walk through a couple of these to give you kind of idea of what these applications require and how HiHAT what kind of features HiHAT would have to support that. Does anybody care particularly about any of this? Right.
Speaking a little bit about and what the expectations is based right now, I'm looking to government for 2 years. And I see that young, changing they are, and I have implemented and I'm trying to make things ready. Tell me what's the expectation out there then?
Yeah, great, sure.
Could you repeat the question before you answer?
Sure, that's a great idea. So, so I'll just talk a little bit about the question about Smith Waterman and how we could see something like HiHAT enabling that aspect. Smith Waterman is a very important kernel in the genomics alignment. You've got two massive genomes, and you want to figure out how does some mutation align to the reference. And it's a very event-based, future-based kind of dynamic optimization problem. Kind of think of it as wave one parallelism. And so you run into challenges with task fusion, so if your tasks are confined grain, you're going to see large overheads. You've got massive amounts of parallelism, so you want enough parallelism to achieve full utilization of a GPU. So I think that in the context of HiHAT, it would need to support very efficient events in order to achieve high utilization of the GPU. Your task grain alignment would have to be tunable at runtime, and also the runtime would have to be adaptable to that for your target architecture, whether it's FPGA or KNL or GPU. And data access patterns are challenging this application, so the whole kind of the building blocks of retransformation and relayout of your data based on the target architecture that you're looking at is going to be a key component for algorithms like that running on HiHAT. And in general, just kind of being able to reuse heuristics for scheduling across different target frameworks and for these different applications, because there are a lot of options for scheduling in something like Smith Waterman, whether you're scheduling to hit some high watermark on resources or just maximize parallels on a GPU, and a community effort like this to really enable reusing those for these kinds of complex kernels. But yeah, so basically I'm here just to reinforce that this is not a research project, that we care about applications, even though we're targeted by runtimes, we understand that those runtimes are targeted by applications. And we're spending a lot of time thinking about what are the key, minimally viable features that we need to support these kinds of problems and many of them.
Yeah, hi, I'm Vincent Cadet. I work at Intel, and actually I'll be wearing two hats today. I work at Intel, and I also work on the Open Community Runtime OCR. So this is a sample flow of how we envision the HiHAT architecture to work. So you start over there from a developer writing a program, and here you can say in applications there's some logic passes, two fragments that do some loops. And the first step would think there would be some kind of refactoring operation where you outline these fragments into function calls that HiHAT is going to be able to invoke. Okay. And then there's a classify operation which goes from this world into a world where now you have a first class object that represents tasks. And here we operate in these different graph service that the building block on top of HiHAT. And if you give it a bunch of tasks, accessing some data, it's going to perform a dependence analysis and tell you, okay, this is how those tasks should be scheduled. There are data dependence, control dependencies, and this is your task representation of your program. Okay. Now that you have your program, you want to execute it on some machine. So HiHAT will provide those enumeration APIs so that the resource service can query those and extract the resource information. And from that, you can build a model, a cost model, right? So you take into account topology, memory hierarchies, those kind of things. Now that you know your machine and that you know how the program is structured, you can go and analyze this. Down select resources, maybe some need special hardware, or you need that much amount of memory to work. And from that, now you're going to be able to have the scheduler do a binding, so put those tasks into some machine and order them. And this scheduler module will generate a bunch of actions. That's going to be the HiHAT call to say, transfer things from here to there, and then feed this output into this input. And there's also a transformation service where if you are to move data from two different hosts, for instance, you might actually take into account the fact that you could maybe relay out this data, and because it maps better to a certain architecture. That's going to be part of all the scheduling heuristic framework. And from there, you just map to whatever HiHAT is providing you. And there's also a notion to record this kind of things, right? So if you were to do this sort of graph into a loop, you don't want to go every time through all of this analysis, right? You want to be able to store that and be able to build on that and amortize your overheads.
Question. So the flow it implies a static test graph. Is that what you mean to imply that? When you talk about dependence analysis, that means you build the entire graph to analyze it.
I think it might be a combination of a number of things. There might be something you learn from the compiler, and it might be something you discover at runtime.
But it's still a static graph that you're looking at, right? At least that's what your diagram implies. I just want to make sure that you mean to imply that.
I think it's open, as in, if you can have a view of your program where you statically derive everything, that's fine. If when you execute a task, inside you make some conditional decision based on the value of the data, whether or not you create another child task, that's going to be dynamic. And so the runtime is to be able to figure that out.
Okay, I just wanted that to be clear. So what the scope of your intended scope was.
Yeah, I don't think that at this time we are closing any doors.
I just make a comment that we recognize. So we want to make sure that they're in a static framework. That's part of the record thing. That you can go through everything as if you were dynamically doing it recorded. But you may also do this as a library that's available in a totally dynamic environment where tasks may be unpredictably being created. And we understood at first why we had that foundation. So these are different services that you can have that can help with this when you need it. That doesn't mean that you doesn't determine how it is used.
Another question over there?
My experience is that so hopefully we have an extreme right? You have to have non-partner so in my experience, that we use to design a graph, let's say a partial curve or something graph that basically encodes all of the coordination and all the parallel fragments. Okay? And then you use that in a tool chain to spit something out that can go to compilers, it can go to main tools, or in our case, Jenkins. Okay? So I'm just confused about that. Could you repeat the question?
So, because maybe one statement that with this classification operation here is something hard, and so you want to know more about how we planning on tackling this.
My question is more why do you that direction instead of the first direction explicitly modeling
Okay, yeah. So I think trying to describe your question, I think that maybe CJ already gave an element of answer, which is that we don't really want to go and mess with how people want to express things. So we are sort of sitting below that. So depending on the tool chain or the high-level languages that are going to target HiHAT, this might be harder to do on some tool chains, right? So thinking maybe if I take the legend region approach, that's something that's going to naturally comes from the tool chain. If you just take C code and you just want to hack it, then it's going to be really hard and easy to do that. That makes sense?
So just to kind of slight spin on that, one of the points you made is you want this to be implemented. And for better or for worse, most existing applications are written in an imperative style in that form. And so essentially taskification is the name for if we take a piece of that, you take a piece of the program, you incrementally pull it out and feed it to HiHAT. A task is just the name of that thing. And, it's kind of a self-fulfilling name. So it's just whenever we pull it out to give the HiHAT is my definition of task.
So the question is, do you expect the user application writer to do this refactoring and classification? Or, I want to understand how we implement this approach. That is one question. The second related question is that how do you, when you're classifying pieces of code, how do you take into consideration the implicit state of the execution of the program before you classify? Do you wrap that implicit state into every task, or how do you coordinate state across?
Okay, so the first question was, do we expect developers to write this? I would say it depends. I mean, preferably you want to have some more of the high productivity things, such as maybe OpenNT or whatever task abstraction that's out there, like Cocos, and do this for you. If you really want to write it by hand, you can, but I don't think it's a good use of your time. And the second question was about all the implicit state. That I think maybe we're going to address a little bit later when we talk about what we expect the user or the tool targeting HiHAT to do in terms of marshalling and marshalling arguments, setting the context for use into the task.
Another comment too, I think it's important. In many cases, if you really build out the whole graph, it would just take way too much memory. So in the implementations that I've done, we never materialize the graph. You just keep it around whatever necessary. And there are cases where you may want to have, if you will, a logical notion of what your task graph is that may get unrolled, right? And with instantiations. And Stephen may talk about that coming up here a bit too about how important it is to be able to support that. Right? But just another key comment. Let's keep clear that the kinds of things that we're talking about, this is all really cool stuff. These are all really hard problems. And what this is all the stuff that you see in these services, all the blue boxes, are essentially things that are happening above the HiHAT user console. So this is basically on a runtime. And we want to build out services that will facilitate that and that people can use and share in common. But we don't have to solve all of those problems before we get going. We do need to make sure that whatever requirements are induced by those issues are comprehended by the lower APIs, so that we don't sign ourselves
into. There was a comment a little earlier about the ability to record operations, and I think that's an important way to think about some of the ways you build dependencies that you might hold fragments that you have opportunities to perform repeatedly. That's something that certainly we see a lot in the algebra, we see a lot in deep learning work when we're invoking the same thing over and over again. So you record the fragments, you materialize the whole graph. The graph may be composed hierarchically of these sub-graph fragments. And so enabling that kind of reporting that you capture a lot of the complexity structure in a way that fits in with the take over. I think that hopefully will be very confident.
I got one more thing now, which is I sort of again, you know, see this at the beginning, right? If you come out of this meeting thinking, gee, that sounds interesting, but it doesn't quite fit my usage model to X, Y, Z, go take those 20 minutes to go to the wiki and write down your usage model so that you can evolve app or you learn about the use cases you haven't thought about yet.
Okay, so moving on. So here I'm just going to talk a little bit about how we approach this with my Intel hat. So at the high level, I think of this as three pieces: the compiler libraries targeting HiHAT, which is the runtime, and then HiHAT is going to have the compute, data management, movement, coordination on top of some hardware. And the sense to me, what's interesting here is that we would like to avoid, so if you have n compiler libraries targeting HiHAT, targeting n hardware, we want to get away from an n by n type of things to an n plus n. And if I think about a little bit more in detail about the HiHAT box, I see a lot of value into those scheduling dependence analysis boxes, because they are always the same thing. There's some state-of-the-art techniques. Scheduling heuristics that takes cost-effective function and optimize on something. It's always the same thing, and we just keep re-implementing them on every runtime we implement. So I think we just need to stop doing that. If you think about more the lower level, like the command layer, then again, it's really nice if you can always target the same sets of API. It just makes a faster time around to implement talking to different hardwares. And here, with me, that is getting more and more diverse. I can have a set of Xeon Phi cards. I can have Xeon plus accelerators, sitting on the box. And it's nice to talk to that through this command interface and also to express interest into specialization. Like if you have NCD RAM or just a notion of a high bandwidth memory, please do use it. If you don't, it's fine. It's work correctly, but it's very bad. And the same thing if I want to use some NVM storage technology. What we want to obtain on the line is this HiHAT task graph that's going to be mapped to resources, right? And here, so that I start with something on the Xeon, and I distribute some work into some specialized hardware, and I aggregate things back. And if I want to do that by hand today, it's going to be prestigious, and most likely it's kind of a four-way solutions. So going back a little bit, trying to merge these ideas we have at Intel and the HiHAT context. So I have the HiHAT box down there with a little some modules, and so I'm starting with a program, whatever that is, however this is expressed and given to HiHAT. For my dependence analysis, I can get a task graph, and now the scheduler can extend that and say, okay, with all the code that's been generated through compilers or that you gave me available as library or something, this is what I can do. T0 can run on the Xeon, and then T1 I give you the choice. There's a file and normalization sitting there. And for this, maybe the user of the toolchain gave you something that says, okay, there's a from the same class you can go through Xeon, but if you happen to have a mix of these, I decompose whatever you do in T2 into something that goes as an FPGA and some post-processing on the file. And by the way, if you can put the NC over there, please do, right? And the same thing, gathering things onto, let's say, a host or whatever visualization, anything like that. And then using the resources and model, now you have a topology and cost, and now the system is going to say, this is really what I can do. So you better use this terminology, and then here you actually do have access to those FPGA and Phi, and so that's why HiHAT with schedule. Also going to take care of doing all the data transfer, which is in this particular case, for instance, at the T2 task level, I don't see that I don't expect there will be a data transfer. But because I map to two different things, I might actually have to do it. And when you program your application, you don't have to think about that. This is just a runtime is going to do it for you. And then you execute this. So just to stress out again, in terms of the data management, this is really nice because now you don't really have to worry. You can express interest in something special like an empty RAM, right? And here in this example, I have a compute task that's using a temporary buffer as a scratch space. And I can free up that temporary buffer, grab a new one, stage a data transfer from my DDR Plus 22 RAM, use it. And all of this was transparent to the user. So it's a really nice product approach. And,
so let's go through another example. Back when I was in Intel, we worked on something called games, and there are different ways that you can run games. But one of them, we had a case that had 40,000 gems, and they were different sizes, but they could be binned into common sizes. We were trying to figure out how to work this, and a lot of the gems were quite small, and we could get overwhelmed by making that many implications and moving that many little tiny pieces of data. So as a way of illustrating this, I wanted to go through this specific example of, suppose I have 5,000 blocks of various sizes that I want to move between some combination of the CPU and GPU. And so one of the things I might like to do is aggregate. So aggregate is not something that you're going to do down in HiHAT. It's a transformation that you want to do above, where you say, hey, let me pre-sort these, I'll find ones that are similar sizes and shapes, put those together, bundle them up so I can do less and move less. So the first thing that you might do, if I have my work that's spread across these, I might do instance resolution. This could be done sort of above the user layer for this. Essentially, I'll find the closest and latest copy of a source, because I may have had a target and lots of people may have been working on it in a distributed fashion. I have to do some bookkeeping to figure out, so who has the last guy? And then find its target identity. I may also want to do alias detection. So it may look like I need to move data from here to yon, but if the hither and the yon are actually in the same place, I shouldn't be doing any allocation. I should be able to say, those are the same. That notion of managing buffers in that way requires the user to be able to say, can I alias these two things, or was I really learning on having different values? That's an example. So then I may pick the transport type. So if it's above a certain threshold, I may want to DNA. If it's small enough, I may just want to use a meta copy. Maybe if I'm going over a network, I may need to pick a transport type based on the different implementation endpoints that I have. I may need to do some address mapping. I have some notion of a logical global address space, but it's actually physically distributed. I have to do some translations, right? So all of these things take thought. All of these things take lookups. They take work. And you want to do those as much as possible once. They're kind of hardish things to do, and so you want them in the layer that does the ease of use stuff. Below that, you've already figured out everything you want to do. You don't want to think, you don't want to do any overhead, you don't want to do any lookups. If you're going to get something that's performant in this architecture, and I credit Sean really pushed through this, you really want to figure all that stuff out so that these lower layers can just be lightning fast. Like there's almost no overhead, no thinking for the stuff that you do. So you figure out all the details. Maybe you say the handle that says, yeah, I figured out how to do this last time. Next time, if I'm doing pretty much the same thing, I can just go and call this. And the common layer may be called directly by some frameworks, or it may be reached through some of these things where you sort of memorize and remember how I did it last time. And so you may also have a mem copy. When I was working on DN5, we noticed that, hey, if you do a mem copy, it'll a lot faster if you get 4 threads at the same time if you use 1 thread. Right? So you could have a different implementation for that. And all you really care is what the functionality is, not the best way to do it. Right? So that's the kind of thing. So I'm going to ask Stephen to come up and kind of lead us through some of the things we have for vendors. We're going to shift gears a little bit in what we're doing. So I have a timer that we're going to use, or if somebody else wants to do it, that'd be great. We have so many people, like 20 people or so, that are going to talk, that if each one of them took 5 minutes, we would narrow it out. If each one took 4 minutes, we would narrow it out. So we're asking people to take 2. And if you need 3, maybe. And so we're going to start clapping at 2 minutes and 45 seconds. And you know, you can shout loud enough over the clapping that it's okay. They'll be engaged. So Stephen is actually, and Sean's going to do this later. We'll just move through the slides, and the slides are all preloaded, and just move through that. So be prepared for us to be moved.
I think the mics are
So use it.
around the edge.
Trying to get the audio a little better.
Okay, so what is this? Oh, I think there's a bunch of slides, but
Yes. Yeah, close it.
These were downloaded. Are you able to drive from there, Wolf?
I can take control, but I'm.
It won't work. Okay, hang on. Sorry, I downloaded them, several of them, but I didn't get the apps one.
Yeah, I would need to take it over to the that's for a while. Really just to stop clapping.
Sure. CJ can't get up the file in for 2 minutes and 45 seconds. Deserves to be booted off stage. Come on. I think I can. I think I can. Can't see these. Let's run off of this for now.
I was going to say, is there
Sure.
coffee?
Yes, go get coffee. Let's do that.
That's a good idea.
Perfect.
What do you want, 5-minute break or 10?
Yep, 5. Let's do 5, and we'll have another one in a bit. Come on, stop that. And you edited this somehow, so you edited this somehow. This is your version of it. Yeah. Okay. So that's ready to go.
Because I did that. Like a combo, like a speaker.
But this is volume?
Oh, no, that's
I downloaded these someplace, but it's, I don't know where it is.
Got it. Okay. And is it about?
Here we go.
well, you need to pick it up.
So just, yeah, but you might get feedback. But I just, this is up.
Oh, I see. Yeah.
Okay. Yeah, we have an issue with that.
We go much higher.
Yes, I will
Okay, well, let's just
look at dealing with that.
Hi. Wait. All right. You can see it. I'm going to talk to him on the phone, but it looked familiar. Did we meet when I was there? Yeah.
Hey, just got here from my talk and just want to see what you.
If you have an extension, I mean, actually, usually have an
Right.
So I think it's the max to look at. Cool. Well, thank you. Thanks for the help.
Yeah. So
I'm well.
thanks for that. So we're going to go through vendors, and then we're going to go through some of the runtime frameworks. And so execute service and and when we start doing that, we're going to do that in alphabetical order.
Sounds good.
We talked about some of the applications we took in. We took some new things up. We made a sampling of which applications we're going to talk about and not talk about. So, yeah, we passed already. Well, we picked the subset. We didn't pick that. Okay. But it's in there. We already passed that phase, so you're just on.
Okay. Sounds good. And we have the phone too, because Dimitri was going to call in and answer any questions. I'm not really a code on it.
Right. You're only going to 30 minutes, so we're going to be 2 to 3 minutes, so we're going to. Does it bring clarifying question?
All right, so I'm kind of new to this whole process of the HiHAT process. Also just so
Thanks. Thanks so much. Hope so.
It's actually AMD. It seems the order is mixed up. It's AMD first. It seems the first slide is actually AMD. I can just go and come back. Okay. Yeah. So again, I'm Intel. The thing we're trying to do, so everybody has the same format here. So the thing we're trying to map to Windows platform, those are the Xeon, Xeon 5, PGA number 9G. In loose term, the platform features, it's heterogeneity, parallelism, obviously, memory hierarchies, specialized memories, and particular accelerators. In terms of the possible things we could do, and that we may see evolve. In software implementation, I could see a number of things happening. Under the command layer, we can start from scratch using some threading and also interface, so more of a shared memory and potentially offload over to some Xeon 5, that kind of stuff. We could also rely on HStream or potentially TPB, the runtime implementation. Under the user layer, we could use OCR, but I see this as maybe a little overkill, considering there's also scheduling and transformation blocks on top of the user layer. But we could surely apply some of the OCR ideas if we were to really strip down the runtime implementation and come up with something else. And above the user layer, there's plenty of opportunity to leverage the existing APIs we have from the different projects. So either using OCR or potentially having NKL or some of the libraries to target HiHAT, and also TDD, more the visible user layer with all the productivity and aspects of it. In terms of assessment of fit and the difficulty refactoring, under the common layer, the split thread approach, I see it as probably a low-hanging fruit to get something up and running. And for stream and TDD, I think it's to be determined, look more that into detail. For everything else under the user layer or above the user layer, I think it's probably a major implementation effort. So we will have to go through some design review first and exactly see what we can leverage and how much work it is. And in that context, also important what CJ mentioned, that things can be incremental. So AMD, I think next one.
Maybe we can have all the speakers just run the thing out front so we can change it.
Good morning, my name is Ashwin from AMD. We want to target CPUs, GPUs, APUs, a whole bunch of platforms. We are also interested in the general whole range of platform features like CPUs, GPUs, wide variety of memory hierarchies, networking assembly types, and so on. So the possible software implementation that we have, it's kind of not clear as to what was under it, all the user layer that we are depending on the actual HiHAT API. But we have two different solutions. One at the low level we have what is known as HSA or heterogeneous system architecture, and ROCm is the Data Open Compute Platform, which is AMD's implementation of the HSA infrastructure. And that is at a low level layer that you can have the functionality of directly accessing the GPU using user mode queues, and you have different memory regions to access to copy the data to the different GPUs and so on. So that's a low-level layer which has queuing models. At a higher level, we have built what is known as PPM, which is basically the task memory interface, which is more of a task-based, and it's more high level where you encapsulate tasks and you build task graphs by describing what the tasks are. So we do see some convergence between ADMI and the user layer, so that's why we are not sure. And there are some functionalities that could go above or below the user layer ADMI. So that's something that we need to engage more with the HiHAT community to understand what parts of ADMI goes above and below the user layer, and what parts of HSA or ROCm goes above and below the common layer. And that's why we are here to engage with the HiHAT community to understand where exactly each of our two solutions fit in.
And Mike too.
Yeah, so this is Edwin from IBM. So I'll just quickly speak to probably recommending is good performance and also portable performance, because they are going to be putting a lot of investment into that programming, and they want good performance and also the program performance to be preserved as they go from generation to generation of accelerator and also across different accelerators. And the other things that with IBM, we've got lots of enterprise customers and have experience with using the different type of frameworks. So relevant to this one, I think that they are going to be asking about how they're going to be managing the data, managing the flow of the data between the host and the accelerator, and also how do they orchestrate the execution of the task between the two. And then the other side is also from experience of the frameworks, the users typically, when things are working well, working as they expected, things are just great. When things are not exactly what they expected for performance or for functionality reasons, they probably want to have some visibility into exactly what's going on underneath the framework so that they could either debug the issue or something like that. So I think that's something that's going to be of interest for us. So we are going to be, looking, the Excel competitive and research team are going to work together to participate in this investigation. Okay.
Yeah, so Adrian, you online? He was sick, been sick for the last few days. Adrian, you online? Okay. So he had done this content, and I want to try to speak to that. But, we've been in communication with them, essentially trying to work with them as an OEM, trying to, they have a lot of significant software stack. Maybe we can also just acknowledge David Lumber Farm, and he's just ramped it up. And we had some other folks from Farm weren't available to be able to join us today. But we've been in discussion for them. Paul Thomas is going to talk later in the meeting here between 12 and 1 for this time, 10 and 11 our time. So thank you.
Okay, I'll be intellectually honest and time myself. Okay, so looking at it from the NVIDIA perspective, it's interesting. CUDA provides a lot of the underlying functionality, but the key requirement of the common layer of HiHAT is that be a very thin, direct translation layer down to the target hardware. Otherwise, the higher level layers that are making scheduling decisions would have to factor in the overheads of what's going on. So the first thing is that we have to look at what other components of CUDA, how do we map them into the common layer primitives in a first-class kind of way. And CUDA has these 3 events and so on. Whatever the equivalents of those are in HiHAT should be, well, we would either have to modify what we're doing if we need to, or preferably have HiHAT actually expose the kind of functionality which I think is pretty common for heterogeneous type communication events and so on. Another piece which I think is very interesting at HiHAT is the need for feedback about information going back upstream to the user layers. We will provide some of that, and we'll have to figure out exactly what it is that the higher level layers need in order to determine the scheduling, and even that type of information, giving that type of feedback and so on. So, all of the components appear to be there. I think for us, it's mainly a question of what do we do at the vendor level to allow to map as tightly and as quickly as possible. One of the things we see in CUDA is an increasing degree of heterogeneity. I'm sorry, I didn't actually put that on the slide. But as you see more embedded systems and things coming online, we're seeing, even at the vendor layer, a lot of hardware to hardware, different types of heterogeneous control, and making sure that what we do for that either uses HiHAT, or maps well to HiHAT, so that you can hand off between a GPU, a CPU, and so on. Very important. So yeah, okay.
We're going to move on to runtimes, and I know we were going to do implementations next, but we're going to switch around given people's availability. So, Michael Wong, are you ready?
Yes, I am.
Great.
we're pulling this up. And if we're kind of going through, again, you can see the slides that are online. And if you would sort of, while the next person is here, would come up so that you're ready to be able to jump through that. We're not going to have time to sort of do the back and forth thing. So you should be able to see what's coming up. And that's fun. This is why we have fast computers, right? So we can all watch. Okay. Any other questions or discussions while we're waiting for this laptop? Any other questions or discussions while we're waiting for this?
So CJ?
Yes.
Yeah, so CJ, I actually have a latest update with my name on. So for my pod, if you can open the one that has with my last name, with my first name on it.
Are you able to share? I will work at that, but are you able to share from on the Zoom? Can you enable that?
I can do that. That would be a lot easier. No problem.
I did not get your other changes integrated in.
Okay, no problem.
We decided. That's really fun. Okay. You're no Zoom better. Do you mind sharing from him?
I'm fine sharing from him. He needs to request host.
Okay.
Or request presenter. So.
Yeah, I'm launching.
At the bottom of the screen it says share screen. If you click that, I should be able to approve it. Right now, let's see what you've done here.
Okay, actually, before this, and maybe we can work this in the background. Ronak, are you ready?
Yeah, I can go ahead.
Okay. Why don't we have you start?
Sure. So I'm here representing Term++. If you don't know what Term++ is, it's an asynchronous tasking parallel runtime system.
Can you try to speak a little louder, please, Ronak?
Model language tasking runtime. It sort of defines a set of primitives on top of C++ that programmers can use to express parallelism. Uses this runtime to coordinate asynchronous tasks in parallel.
Hey, Ronak?
Yeah.
Unfortunately, the sound isn't great. If you can speak louder, that would help.
Sure. Is this any better?
Yes.
Okay, perfect. So as I was saying, we want to target different sort of HPC systems in particular. So we look at mostly the enterprise class, big DOE. We're also interested in regular clusters and even smaller parallel on desktops and laptops and stuff like that. So URLs are up there. Some sample applications that we have in Chart are Mandy, molecular dynamics application, Changa and astrophysics, OpenAtom, which is quantum chromodynamics, and a bunch of other ones as well. In general, all the functionality that's listed as part of HiHAT, we're fairly medium to highly interested in. One caveat is that we have code that does a lot of this stuff already. So unless we see a big value, it would be a bit difficult to justify a full refactor. But we're definitely participating. And apologize, sorry. And you'll have to see, particularly for things like heterogeneous execution and different kinds of data movement, to try to find the best places on the memory hierarchy and to manage data transfer and things like that. Can you go to the next slide? So in general, the things that we're looking for the HiHAT layer are, one thing is that the Term++ runtime is fully asynchronous as much as possible. So any interface that HiHAT presents, we'd like to be asynchronous as well, just for ease of implementation. In general, we want things like topological analysis. So this means trying to identify and place things on the network of a machine. Ideally, we would have things for network primitives, if we're talking about communication. If we can target multiple implementations of network layers or different kinds of RDMA and things like that, that would be ideal. And like I said before, really interested in different sorts of data migration and management for accelerators in terms of placing data in the right spot, figuring out where to execute tasks based on where data currently is, and things like that. We also like, ideally, to have detailed implementations on where tasks actually execute and make sure things are low overhead. You can go to the next slide. And then more on the implementation side, one thing that features very strongly in Tran++ is a dynamic task object mapping framework. So in general, use this for load balancing, but this can be used for lots of different sorts of optimization for tasks and hardware. Basically, the way this works is that you can measure some metrics about load, about power and energy, about who different tasks are communicating with. And then we have a set of algorithms that determine different layouts that might be better given the application and system constraints. So the setup for this is that somehow from the user side, we'd have to get some notion of load. And also ideally to use this dynamically in an online way, some way of migrating objects or tasks around. Ideally, we would want,
Sorry.
After that's provided.
We were muted, so he couldn't hear us. Okay. Okay, so next up is name in-person remote. We got somebody talking about SYCL. Code play dudes.
Can everybody hear us? I want to make sure we're back off mute. Are we back off mute?
Can folks on the phone hear us?
Can you switch over to the?
I can hear you. We may still be on mute.
Okay. Can I switch to my screen?
Yes.
Great. You have to turn off your screen then. Thank you. Thank you.
I'm not sure how to get that back. Sorry? F5. Okay.
Is he driving out?
I don't think he's driving. Is he driving?
Yeah, that was cool.
So you want to go to Zoom?
Can he request?
Michael, are you on?
I am, yes. It's a good screen. I can just.
Try again.
Thoughts?
And this somewhere you got a microphone hot.
I think I'm still having trouble because it says the other participant is
Which one
sharing.
is Zoom? How did you set this up? All right. Michael, we're having some difficulty. I know that these aren't the slides that you want.
That's okay. We
Is there
can
a way that we can roll up with this?
Yeah, that's okay. Just we can work with what you got. It's okay.
I'm getting a request for him to host. To share. He clicks on that share screen.
So let's be expedient. So
Yeah,
sorry
that's
about
fine.
that.
Yeah, no worries.
All right, I'm on.
Okay, so my name's Michael Wong. I'm a member of the C++ Standard Committee, but also a member of a number of other committees, including Chronos, and which develops the OpenCL and the SYCL standard and HSA, and also currently working at CodePlay. I previously was involved with a lot of heterogeneous work at IBM and at OpenMP. I want to talk about SYCL right now as a runtime, and as a runtime, it is talking about the Chronos standard, and the implementation is the compute CPP that CodePlay implements. It is a language that is a pure C++ language that is meant to work well with C++ 11, 14, and moving forward to 17. It already implements parallel STL. It is meant to be used as a drop-in replacement for C++ for advanced modern C++. So it can essentially implement the entire software stack and can map to any offload devices. There's a URL called ChronoSickle that you can easily Google for. And there's also a community edition that you can download. When CJ and I talked about what type of functionality is of high interest to us, we feel that for us, data movement is the #1 thing, because one of the things that Sickle distinguishes itself is that it uses implicit data movement that is defined by a data directed acyclic graph using essentially a data flow algorithm. We also feel that data management itself is extremely important. And finally, we think that the ability to enumerate different kinds of resources and topologies are also important. This is from the specification itself, because the specification is part of an open standard. We work really hard to support that capability in the specification. The other thing of lesser or declining importance are things like, but not nevertheless are important, are things like synchronizations and communications, and tooling, tracing. Talking about whether the implementation can be refactored easily into HiHAT, we actually designed it such that the data movement and the data management can both be easily refactored itself, whereas the other parts are varying degrees of being able to refactored. So that kind of covers how it could easily or reasonably be adapted on top of HiHAT itself. So next page, please. Can we go to the next slide? Hello? Can you guys hear me? Yes, we can hear you.
This is Galen on the phone. I can hear you.
I think we lost the group at the site.
I think so.
I think they are just on mute. I think they can hear us, but maybe they should confirm.
I don't see the screen though anymore.
Yeah, I lost the screen as well.
They were connected with two users, and only one is left now. So my hunch is that they lost connection.
Mm-hmm. I think you're right. Well, now we can all say what we really think. No, yeah. No, I'm joking.
No, really, I want to know what you guys all think. Where is this going?
Let's fork.
Well, I think there's some merit to exploring like lower level common layers.
But it's basically trying to do an interoperable runtime that is adaptable to any targets and any language. This is a really ambitious goal, right?
It depends. I mean, I think it depends if you focus on kind of the lowest level mechanisms and didn't get involved in like policy or anything else. Maybe it's possible, right? But I don't know.
They're trying to have swappable components that you can swap out or swap in. So that's why they're asking us whether there are parts that we can refactor out. So let's say you want to refactor out the data movement, then they can apply their data movement modules inside in place, right?
Mm-hmm. Mm-hmm.
And that's basically what I got from a long chat with CJ last week.
Yep. I mean, I could see this as being useful. So, like for instance, we hit a lot of problems with interoperability of different threading implementations. And it would be nice if everybody agreed on something other than like the P threads, because a lot of the things we want to do require user level threading.
Yeah.
But then you get into an issue of, well, who does resource management?
Yeah, there's resource scheduling and performance portability. If you try doing this, are you going to be able to maintain your performance?
Yep.
That's going to, I mean, they're hard enough to get as it is the minute you raise the abstraction.
Yep. I mean, if we just said all we want is like a low-level user-level threading library, right? I could see how we could do that, particularly if we said each like component would partition up some number of resources and then just run with it. But you know, almost immediately you say, well, that's not good enough because we want to be able to dynamically, you know, resize the amount of physical resources associated with any component, and then you get into all kinds of scheduling and policy issues. And
yeah.
But at least you then can start working on those more difficult problems, I guess.
I mean, that there are a lot of these different implementations of the runtime now for C++ at least, right? There's Cocos, Raja, Charm++, UPC++ is also doing it, HPX, us. They're all trying to go for the holy grail of performance portability. And to be honest, I don't think anyone has really reached it. I don't know if anyone ever will. I mean, it's one of the most difficult things to do.
Yeah, yeah, we've seen it like in terms of data layout, partitioning strategies, right?
Yeah, they all have that. Yeah,
all
I mean, Cocos is really strong in data layout, and similar Raja also tries to use partitioner strategies to improve the cache coherence aspects of it.
Oh, we got a message from.
Yeah, they're taking a break for 5 minutes. I think I broke them. I feel bad. Did they say who is actually there?
I don't know.
No, I don't think so.
I think to some degree OCR and HPX were attempts at being a universal runtime system.
Yeah. Well, that's what part of my job is, trying to analyze these and try to inject the best model I can into C++ standard. So C++ standard is now trying for a heterogeneous model, and I'm the chair of SG14. So part of that is heterogeneous computing at low latency. And we're looking very carefully at HPX, SYCL, Cocos, and Raja as the primary examples for C++ to have an integrated heterogeneous model. But they're so, I mean, at some level, I mean, even right now, we're struggling to find the right terminology to talk about them in a coherent way, right? And what one group says is their synchronization or mutual exclusion is different than what another group mean when they say that, because part of that we figured out is the fact that different models have different memory layering and different memory hierarchies. And these things have different meanings depending whether you're in some local memory hierarchy or some global memory hierarchy. And part of the problem is that C++ right now really only recognize essentially a flat memory model with no real understanding of memory hierarchy. The memory model itself doesn't understand these things that has to do with different forward progress guarantees that are in different memory hierarchies. And so we think that, you know, to even begin to talk about it, we pretty much have to start with the difficult task of partitioning C++ into being able to support different memory hierarchies. I mean, there's no way to do that. I mean, there are ways to try to put a bandage on top of it, but it would still be kind of a bandage. I don't know.
I mean, is that does C++ have a complex with respect to putting band-aids?
No, no, we put lots of band-aids everywhere. Usually,
can you stop using global state inside the STLs?
Well, no. Well, that's the point, right? I mean,
we're hitting some with thread local, so we're hitting some issues with like the use.
If you turn on TLS, half of STL is going to be kind of broken.
Yep.
Right? I mean, it's not going to understand these global states.
Yep. Well, and a lot of the tasking
a paper right now to talk about that in a more succinct way, because we find TLS is a big problem, and we look. Awesome. We totally abandon TLS, but we think we can because the industry and HPC uses it a lot. You know,
we're beating people over the head here not to use it.
Right. We want people to stop using it because it's a big problem. I mean, OpenMP ran circles around itself trying to create these things called what the hell?
Thread private.
Thread private, yeah. That is essentially a TLS that lasts forever. So, yeah, we have the same. C++ standard is looking at the same problem. I've and a couple of other people have been writing papers to talk about, you know, all possible ways to handle TLS in the presence of concurrency and parallel and C++ parallelism.
Huh. I'd be interested in looking at those. Please.
Send me email if you guys want to look at those and talk about it. I mean,
what's your email address?
You should be able to find me online easily. I'm Michael Wong, SG14 chair. Just look for Michael C++.
Yep.
Cool.
Thank you.
Also the
topic is quite interesting. Could you maybe post it in the group chat here? The title of the papers.
I'm gonna have to find them because there's so many different papers, but they're almost up, they said. What I am interested in right now is talking to a lot more people about what kind of heterogeneous C++ model they in standard C++.
Right.
Hey, maybe this is the time for me to take over the slides. Yes, I can do it.
So actually, there is a way of sharing multiple screens. If you go to view options, you can see the different screens, so they can put your slides on, Michael.
I have new share.
I can switch between your screen and
you can screen.
Yeah, there is I have something on the top of the screen called View Options. If I open up, I can see.
View options.
How about now?
Hi guys, we can.
Folks on the phone hear me now?
Yeah, we can hear you.
Awesome. Had to press all the right buttons in the right order. Okay, so which one are we skipping to?
We're just finishing that slide that you're showing right now.
Actually, we're going to skip ahead to our stream due to scheduling concerns. And the thing I was trying to say on the phone when nobody could hear me was that we're going to have to go pretty fast. Okay. And so the new and improved time limit is 2 minutes, and it's hard limit.
Go for it. Okay, thanks.
So our stream coming up as soon as I find it. How about that one? No.
I think you have old slides.
Okay, just talk.
Okay. So when the good slides come up, it shows some, it has some results. So our stream is a collaboration that we did funded by Department of Energy and DARPA, working with Intel, ENL, Rice, and so forth, targeting OCR and other runtimes. And so we're doing the function that Vincent alluded to, which is taskification. So we're a high-level compiler. We can take in sequential C loop nests, tensor calculations fit within that framework written in C, and do the parallelization to a task graph, automatic parallelization to a task graph. So doing the taskification. So some of the nice features are automatic generation of self-unfolding task graphs, dynamic task graphs. So the compiler generates an OCR program that will self-generate as it's running automatically from the sequential C. It's also doing communication generation, scratchpad memory management, and so forth. So we're getting really good results with that. I think probably the compiler that we've written has generated the most OCR that's out there, and also high performing OCR that really shows the benefit of the event-driven task framework. So if someone would like to try it, they can let me know. We're interested in targeting HiHAT standard directly or the runtimes above it. And we targeted a couple of other runtimes, Swarm, some pthreads-based runtimes, GPU-based event-driven runtimes, and we're looking forward to targeting more. So, thank you. Any questions?
Okay. Thanks. Sorry about the slides. We'll make sure the official slides are actually in the version that CJ is going to pull up or online.
That's not it either.
Back
Sorry.
on track, so we are now?
No. Yes.
Yes. In the slide, we'll appear behind you.
Okay. So my name is Janine Bennett. I'm from Zambia National Labs. So I have a software stack here because just to disambiguate what Dharma is from what HiHAT is. So at first cut, they sound like very similar activities, but in fact they're very synergistic, and this is to highlight that they're at different levels of the software stack. So what is Dharma? It's a C++ abstraction layer for tasking runtimes. It facilitates the expression of tasking and maps to a variety of different runtime system technologies. And so Zambia's HTM program, which is part of ECP, is using Dharma to explore course grain tasking runtimes in the context of their next generation codes. So very briefly, Dharma captures is a very thin layer that captures data task dependency information, and runtimes can call into the backend API to
No,
control.
that's just kidding. You got another minute.
To build the data, and they control the construction and execution of the data. We go to the next slide. HiHAT is actually much lower in the software stack, so it's between the hardware and the runtime. So you'll note that Dharma has this notion of a glue code as well as runtime, because there's many different runtimes out there. They all have varying levels of capabilities and standard levels of the software stack. And so this glue code is targeted for each of the different runtimes. So if you go to the next slide.
We will in a second.
If you go to the next slide, basically you can see through our responses that we're very interested in all of the different things that HiHAT is going to be exploring. And our backend API is very amenable. We're interested in understanding the long-term trends and where best practices are leading. So our backend runtime-facing API is highly amenable to refactoring. We want you to design that with the runtime system developers. And then I have NA there as well, because there may be various different runtime system components that are stuck in there. So Charm++, HBX, various of these different technologies. And so the dependencies are really going to depend on the dependencies of those blue layers. So again, you can go to the next slide. And basically, from a dependency perspective, I'm trying to remember what I wrote it. Basically, everything kind of depends on the blue layer. Dharma tries to, at the programming model level, be very generic and not impose a lot of restrictions, so we can explore the different runtime system technologies. And so, from an interface perspective, C++ is ideal. Other languages are okay with the thin wrapper. And in terms of general requirements, right? Again, we want to explore a variety of different layers. We currently have a wide range of performance. Our applications are targeting using Dharma in terms of coarse grain tasking. We know our runtimes underneath us provide much finer grain tasking, so ideally we would want HiHAT to support that. And in terms of ease of use, we wouldn't have any requirements for the runtime kind of below, but if anything's going to make its way up to apps, we want it to be
Yeah, we'll talk about Extensor. We can React, the output author, it should be on the phone. It's basically a hierarchical tensor algebra library. Basically, it targets several applications for the Florida Summit system. So I think in the longer term, we're interested in HiHAT's capabilities in terms of asynchronous tasking. Basically, we custom tasking, asynchronous task launch, and asynchronous memory transfer for this application, and we like to program all the major HPC platforms. Okay, so requirements, we like basic building blocks, APIs for compute, asynchronous compute, and asynchronous data transfer between devices. We like to control the task placement, dependencies between tasks and transfers. Also, device cost models, and we do with the launching of the tasks. And so we like portability across all HPC platforms, and because this is basically the DGEM base, DGEM is the main kernel here, so we like to get a very high fraction of performance principle that should be possible for DGEM type operations. And also, we like to be able to write code once and not to have, for any tool, have a we like to minimize vendor-specific tuning. Like to have a single code. And also ease of use, just as an example, this the Kubernetes API is very clean and intuitive design. So we like to develop all out.
20 seconds.
Okay, and it's basically some of the same things. On the short term, we're pretty much on a trajectory to the end of the year. For summit for preparedness, so we won't be interested in this presently, but in the future we're interested in a tool to handle these issues, data movement, and compute, and remote implementation. But basically, we want to be able to watch asynchronous tasks and control the data management.
Thanks. Okay, let's get off to Antonio.
Hello, I'm here to talk a little about Icon, which is the hybrid heterogeneous attribute graph generic library environment, which is a new project for the So the idea, as the name of the project says, came up with that name. Our focus is supporting efficiently graph algorithms, and in particular the graphs. The key point of the project will be adding this dual view where the graphs are coupled with tables, the possibility to shift across one view and the other. So this, of course, brings a set of requirements on the runtime, because we need to support the requirement graph operations, but also table operations, and possibly support a variety of platforms. Sure, the custom chips that will be running there, but as any, let's say, as any library developers, we want this to be able to be used also outside the specific projects. Yeah, all but what is used around after the project. So certainly there is an interest in HiHAT for adding the real support, for adding support for the data transformation, data management, and I put the level of interest on Medium for more feedback tools and enumeration, because we start from given platforms. The idea is this will become important, much more important as a key development. So you can go to the next slide.
Okay. As quick as you can.
Yes, sure. I just listed the set of requirements that we have. The big thing is I've seen that we have a lot of use of active messages with variable size arguments and buffers. And of course, we want to target C++ and have a general library. And to do this, we bridge basically the best of breed. I have in the slide a couple of information of the different types that we're working on, in particular GFT. But we are basically trying to bridge the work that we did for single label graphs, OCR, and C++.
Okay, that's all we got time for. CJ, is arts a separate thing, or is that was part of this? Is that a separate 2 minutes? Or? No. Okay, Mike. Sorry, we're rushing everybody equally. So, I'm going to be mean to him. He's going to talk about slides. We'll look at the right version of slides.
Yeah, slides on me, so you guys just have to. Yeah, so I work on Legion. I'm not going to talk about Legion all today. Legion is a core system, designed for supercomputers and data centers. That's important. And we care about the data center world also. If you want to learn about Legion, there's a URL there. You can look at the slides later. I think in terms of HiHAT features, one thing we see on the right here is that, in terms of metadata refactoring, we're willing to rewrite any piece of code that's proven to have a better implementation in HiHAT. Unlike all my application people that I deal with that are unwilling to write any other code, I'll do the exact opposite. In terms of interest, I think we have interest in pretty much all the different aspects of HiHAT, especially in tools and tracing and debugging. I really want to see, a really good effort on that. Really be able to dive into that level. CJ, do you mind advancing slides, or are you just going to make me wait and keep talking? Thanks. Yeah, so in terms of requirements for HiHAT, I think we're interested in a couple different things from the interface. We want to see LVM-based dynamic task registration. Let's see, I think every feature in HiHAT has an asynchronous implementation that gives us some sort of event back that says, when we're actually ready to actually use our features or use the results of our computations. Doing all this off of memory. In terms of ease of use, I think we have absolutely no requirements on HiHAT. I'm actually interested in HiHAT being as verbose as necessary to communicate all the important information about how I want the code to execute on the machine as possible. So I really care less about how pretty it is, especially the common layer. We just effectively use the usability of the common layer. We sort of sit at the same level as the user layer in HiHAT. So I really could care less about ease of use. In terms of performance, we're interested in tasks that are efficient down to about 10 microseconds to granularity. Anything below that is nice, but it's really just icing on the cake. We're really interested in about 10 microseconds. In terms of generation or generality, I really want HiHAT to be able to do tedious passing style tasks, be preemptible, be able to target all kinds of memories and monsters, and we also want the ability to wash tasks that have either been predicated false or have bad fault or something like that.
Okay, thanks, Mike. So CJ says we're going back to the grid tools now, because that's now in this version of the slides. Okay, grid tools.
Okay, so grid tools is C++ library. Okay, we are already at this slide. Perfect. So it is meant to for computing on stencils on very complex applications like weather and climate kind of application. It is sometimes defined as a domain-specific embedded language, in a sense that you can express producer-consumer relations between these stencils, and also you have many other features that our users actually want, like runtime selections of what stencils to run. It is based on C++ meta programming for efficiency. And there is a clear separation between the front end and the back end. From the back end point of view, we can basically do whatever we want as long as we can compute those stencils. So we do a lot of loop fusions, vectorization, etc. But to be able to handle real application, we also need to handle other stuff. So we have libraries for boundary conditions, for Halo update, in order to avoid several of the copies between different spaces. Can you switch to the next slide? So in Switzerland, this is also part of the PASC initiative in Switzerland, where we are funding a lot of activities in molecular dynamics, material science, weather and climate, and others, in which we are trying to force our users to switch to task-based approach and C++. I think I stop here.
That's perfect timing, thanks. Okay, we're gonna do, I believe, OCR next. Let me hand the microphone off while I get the slide right.
Okay, so talking about the implementation runtime, there's two aspects to it. There's a part of it is an API and a specification for efficient programmers or compilers to target. And the other one is the runtime implementation. And we can actually see how both of those would map to HiHAT. So there's a bunch of links and everything. But you're simply on one side. So just a thing I want to highlight the data component. That's something that I think there's still some opportunities there to do in software improve. The thing I really want to stress out is the profiling and tooling, tracing, all this kind of stuff. I think this is a really hard problem, and all the runtimes have the same problem. So it would be great that by committing HiHAT, we actually have this common effort. And also just about the big internal stack, it's actually having tools that we can insight into why I love that kind of things. So yeah, so as I said, I think these are an old version, but so talking about OCR, we try to see so that HiHAT doesn't miss anything. Two different approaches. If you use just the OCR APIs and you target the user layer, so you don't have any more the runtime versus the runtime, the OCR runtime in play. What are the things that we rely on in this OCR runtime, such as tagging and naming mechanism? That's to say that the tasks can sort of establish this is the data in the same X, and some of the tasks will actually use that. And also everything we did in terms of shared distributed data structure in the OCR runtime, where is this going to be? Can I have easily some interfaces that I can reuse? Also, a short of hints, trying to convey the meaning you got from the tool down to the runtime, like this would work better in the high bandwidth memory kind of thing. And then the common layer is already just, when we, what type of network support do we need, the asynchronous versus synchronous layer, of course. And yeah, don't have any particular each of these requirements. We are target for higher level languages.
Okay, thanks, Vincent. Okay, so let's see, we did our stream. The next thing in the slide deck is the Raja folks who unfortunately weren't able to come here. They sent us this slide, and so I'm going to give you maybe 30 seconds to take a look at it, and then I'm going to steal all the rest of their time for me talking next. So that, and I guess I have one more slide here. Okay. And it's all online if you want to read it more carefully. Okay, so I'm Sean. I'm actually going to cheat even more. I'm going to talk about Realm twice. And the reason I'm going to do that is that, in some sense, Realm's mission in life is nearly identical to the HiHAT Common Layer's mission in life. And so my ideal outcome, and the thing I'm actually actively pushing for, is for the common layer of HiHAT and Realm to be basically just syntactically isomorphic. So I'm interested in all the pieces, obviously, and the one I want to call out as the one that I think is especially tricky is I think we're going to get a bunch of sticking points with the way we do synchronization and communication between the different vendor components. I think that's going to be one of the trickiest things to get right in the common layer. We've thought a bunch about it in Realm, and so I'm trying to make sure that my positive and negative experiences from that are transferred. As far as what Realm needs, if Realm ends up being above the common layer, the main things that we're looking for in the common layer are a clear separation of policy and mechanism. So the idea that Realm or things above the HiHAT common layer have the precise control over what they want to do. And as Mike said, if that requires a little more verbosity to say exactly what you mean, that's something I'm okay with. And then, but you want the HiHAT common layer to take care of all the actual implementation of the mechanism so that you're not duplicating that code in every single client. Performance transparency came up. It's very important. If you want to be able to target these systems, they have to be predictable. And then true asynchrony. When I launch a boatload of asynchronous work into the runtime, I need it to treat it as complete and independent work and not stick it in a queue and get stuck when the thing on the front wasn't quite ready to run yet. So that was Realm as a potential client. If it turns out that the common layer ends up coming in above what Realm tries to do, then Realm now becomes a possible implementation for HiHAT. And in this setting, we're interested in targeting basically any kind of processing element that exists, so CPU, many-core GPU, but also think of things like Python interpreters or Lua interpreters or FPGAs or anything you want to run a computation on is the sort of thing we want Realm to be able to target. We're interested in basically all the features of the common layer. This is not an accident. And I listed a number of possible sticky points between ways Realm chose to do things and way other folks might. That's all I have time for. Next up is Swift.
Yeah, hi, can you hear me?
So do we have Mathieu on the phone?
Can you hear me?
Yes, go ahead.
Yeah, great. Yes, so just a very different perspective here. They're mostly end users, so we are developing an astrophysics code. And then for the purpose of the code, we have to develop our own open source tasking library underneath.
So, Mathieu, the audio is not great. Can you try being a little closer to the microphone, maybe?
Is it better now?
Way better.
Way better. All right, great. Sorry. So we are more of an end user side of things. So we are developing an astrophysics code, and for the purpose of the domain decomposition and also because of the load balancing issues, we had to work on a task-based framework. And that started 5 years ago, so we had to implement our own mechanisms, which is a very lightweight C library of about 2,000 lines of C code. And we are basically targeting large cluster of x86 GPU or power architecture. And I don't know if you want to go to the next slide, just in terms of what we are interested in. So what we're mostly interested in is not having to port our own library to every possible machine in the world. So having some common framework like HiHAT would be perfect. So the key requirements from our perspective is really high-level task, acting on large chunks of data. We're not really interested in really small tasks. We want a task graph which is reusable. We don't want to spend time rebuilding the graph every time step. And also the ability to run a subset of the tasks that have been created previously. We also have, our library has to use these conflicts and not only dependencies. That's crucial for our work, and that would be very important to us. And finally, we have also asynchronous communications between compute nodes. And so this is now an overlay over MPI, but we don't really care what comes underneath, but it's really important for us to be able to asynchronously work and transfer to either GPU or any kind of other accelerator. And finally, that's maybe less on a side note, would be interaction with the file system to the extent that we have some tasks that actually do input-output in the middle of other more regular work operations, and so that shouldn't be a limitation that preventing, the system, the runtime should not prevent access to the disk in some ways or another. Right, that's all I have to say. Thanks.
Okay, perfect timing. Thanks. Okay, next up is Dylan talking about TensorRT. Hi, TensorRT is a deep learning optimization engine that we're building at NVIDIA. So the idea is that we will slurp in a network that's been trained in some neural network training framework, and we will optimize that offline to find the fastest possible execution schedule. So when we're doing the offline optimization, we're interested in enumerating what's in the system, and that may be CPUs, GPUs, or potentially other kinds of accelerators, tuning over multiple possible schedules, being conscious of locality and data transfer time, and then recording that schedule so that we can make data. We have many use cases, spanning data center, automotive, real time. So when we're in real time, we're interested in aggregating tasking to minimize resource usage on low-end platforms. We're also interested in very deterministic, predictable schedules for things like automotive. And then when we're in data center, we are interested in being a good citizen so that we can be assembled into production pipelines using a common infrastructure. Wow, ahead of schedule. Cool. Okay, so next up is John Stone.
So I'm working on BMD, which is a molecular visualization and analysis tool, and it has built-in tasking mechanisms that I developed many years ago that has evolved over time to encompass things like GPUs. So one of the things I'm looking for out of HiHAT is to keep and extend the range of platforms and targets. Some of the things that I'm really after are the top 3 items: data movement, management of different kinds of memory pools, all the synchronization and events, lock queues, and things like this. In my answer to remote and local invocation, I sort of put that as low, in part because I'm not really sure what HiHAT might encompass or may not encompass in a particular area. And similarly, in the areas of debugging and so on, I think these are potentially very important, but it's not clear to me what those APIs might look like. So it's hard for me to answer to what degree I might be willing to refactor. Generally speaking, refactoring doesn't bother me at all. Because I have an existing runtime system, I can easily rewrite the low-level portions of that using the bottom layers of HiHAT. Next slide. And so what I'm really after is something that works well with C and C++. One of the things that's unique about BMD, is more like consider other applications in HPC, this is more of a toolbox. There are hundreds of different algorithms, not just 1 or 2, that matter, and how much they matter depends on the user. And the user is going to assemble pipelines and analysis workflows by themselves in high-level scripting languages, and those are going to be generated at runtime. And that sort of dynamically runtime created task graph is something that HiHAT needs to encompass for us. And then, of course, there may be challenges with some of those task graphs because of hard limits on memory capacities, on chip memories, things like this, scheduling. I agree completely with the last presenter's concept on I/O. That was always an issue for AMD. There's I/O all over the place in the things that we do. And I want the low-level primitives in particular to be very performant. The high-level ones, I can look at various issues there, but the areas where I might dive down into the guts of HiHAT, I would want those to be as faster than what we wrote ourselves. And so I think that's how I summarize it.
Thanks, John. And you want to close up, right?
We're gonna go run into the implementations next. And is Halim on the line? Okay, so Carter, can you come up next?
Okay, so I gave a presentation yesterday on the progress we made on the implementation. Okay, so scope of it, we're looking for completely on-node, shared memory, and dynamic. This is right brought up earlier, dynamic task stack, where you're actually creating tasks on the fly, on the GPU, or on whatever backend it is, CPUs, Intel, KL, Power, GPU, etc. So we have write once, execute, compile, and execute anywhere. Dynamically creating tasks and new dependencies on, and we're looking at very fine-grained tasks, opposed to coarse-grained, fine-grained, 200 hops inside of a task to be able to get performance out of this. So very low overheads. HPC tasks is available on purpose now. Let's go to the next slide. Okay, so on the data movement, if you can get data movement actually working across different memory spaces, then we could extend these task stacks to go across heterogeneous architectures rather than being sitting inside of one particular architecture. I'd like to see that. If it ever happens, I can use it. Data management, very critical for us to be able to manage within a memory space. And with these specialized tools with extremely high performance, especially when you're creating and destroying tasks on the fly, it's got to be very good. We need thread teams. So we're doing thread teams on tasks, but we need very good synchronization communication mechanisms. I deleted locks off there because for the kind of resolution and fine-grained tasking, locks are out. So queues, collectives, iteration. We only do remote local invocations. Very critical to us what kind of resources we're on, topologies, resources. I'd sure like to see some decent tracing callback tools, but we'll see when HiHAT does it.
So I'm going to talk about two things that I think from the HiHAT perspective are more or less could be considered infrastructure, sort of humble things. The first thing is QThreads, which is a usual tasking library. So probably the biggest thing that QThreads provides is full empty-bit synchronization, like you find out Creds and T. It's a C library, so it's pretty straightforward, goes through compilers real easily. So our main customers right now are using the default tasking node layer for Craze Chapel runtime. We've been working as a Cocos backend and also inspired the other work on the tasking backends that Cocos has. Then he is multi-threaded graph library, and then currently we're also looking at, we're just a non-node threaded library, how we interact with communication libraries, whether that's MDI or AMT type operation that HiHAT we run. We're on GitHub BSD license, been around for 10 years. The other topic is Norma, Node Resource Manager. Unlike you, it's very, very new. So I think the idea here is to manage resources on the node through what makes like a subscription where we're operating different programming models. So I think that if we don't use this particular thing, we're going to need something like this. So I don't really care if it's what I've done. So what I've done is pretty simple. Gen layer on top of HWLog, but I think we can all agree we need something to arbitrate between different programming models.
Great, thank you. And next is Pasha online.
Can you hear me?
Yes, you're a little soft. If you can speak up, that'd be great.
Any better?
Yes.
Okay. Hi, I'm Pasha from ARM, and could you ask to talk briefly about networking libraries it's working on? So this project is not just ARM, there's many other companies involved in this, and I just represent the effort, which is UCX. The root of UCS came from Oak Ridge National Laboratory. It's where we started the project. And on conceptual level, it's based on ideas that came from OpenMPI, PAMI, Melon, MXM. Essentially, we started it code-wise from scratch, why ideas have been developed probably for a decade, if not more, into new, highly optimized networking library. with the goal provide open source and vendor supported network interfaces for various high performance communication libraries like MPI, OpenSHMEM, and also we have been collaborating with SaaS-based runtimes. It's also used outside of HPC space for other markets, more enterprise and cloud and so on. But in this talk, I will focus only on the HPC space. Next slide, please. So this is a high-level overview of the library, which essentially consists of 3 main libraries. On the top level, there's libraries that we call protocols, which implement relatively high-level API for network communication. It's relatively easy to use. It has essentially a set of API for message passing interface. There is one-sided communication API for PGAS and PGAS, OpenSHMEM, and so on. There's support for active messages, and this API is mostly target task-based runtimes. And there is also work in progress on IO-driven interfaces, streams, and so on. At the bottom, the protocol layer is built on top of transport layer, which is really low-level API. It implements only the part that's supported in hardware. And whatever is not supported in hardware is simulated in protocols layer. For example, if you have devices that only support send receive, but you need put and get semantics, is something that protocol layer can simulate. The same true for atomics and so on, and tag matching. On the low level, we have native support for modern analog devices, pretty much all types of transports. There is also support for OFA services that open support for other interconnects. Oak Ridge National Laboratory have been developing support for Cray. There is support for various shared memory devices, GPUs, and so on. So on the side, there's service libraries that manages modules. And I think this one particularly can be useful for somebody that want to develop a library based on modular compatible architecture. Next slide. And essentially, I just want to highlight all the organizations that are involved in this effort. Any questions?
Okay, great. Thank you very much, Pasha. And
excuse me, I'm Halim from Argonne. I might have missed by my turn because I
great. Yes, we will come back and catch you here.
Yeah, cool. Because my battery died.
Okay, you're on.
Awesome. So I'm Harry from Argonne. I will briefly introduce Argobot, which is aimed for on-node concurrency. We don't do multi-node stuff. So we basically care about CPUs, and we also care about memory kinds and heterogeneous memories, but it's just a plan right now. We don't have any concrete code yet. And so in terms of functionality, what we give to the users is full control over thread management. We provide very fast thread creation and joining and synchronization and all that sort. And also we basically give full control over scheduling and managing all thread pools, as opposed to basically making decisions. So this maps cleanly to the common layer of HiHAT, since we don't take any decisions, but we give fast mechanisms. And so we also work with other threading libraries like uthreads to kind of unify and find common goals, so that we unify some API, so other user layers can basically have some kind of standardization. So that's the introduction. If you have questions, let me know.
Okay, great. All right, thank you very much. And we had, let me just go a quick view here. Let's back up to where we were. So we've had a number of other folks that had wanted to present something and weren't available today. So folks from Parsec, for example, and others that had interest in this.
you could mention that the Raja guys, there's a big thing going on in DC, so they had not been able to be done. So one of the questions, let me just ask for a shout out. Are there others runtimes that you think have been missed today that you're not seeing up here that you think we should be especially reaching out to? So we've started talking to the Uinta guys, they're not here. Others that you think of? Yeah.
We're developing a reference called the hybrid classroom strategy. It's a totally different approach to how you do task scheduling and define tasks in the graph explicitly. So the actual analysis for mapping out relations to the graph goes directly into implementation. And instead of creating tasks dynamically or scheduling tasks on threads, we combine threads to tasks and send data tasks instead. So we have specialty tasks for handling things like CUDA. We have mechanisms for scaling long execution pipelines. And we provide a separation of concerns by having bookkeeper tasks that deal with state and memory management tasks for memory and locality. And we're working on scaling this to clusters.
Okay, great. I think that wasn't able to be heard by the folks on the phone. So another framework called MIT, well, maybe you can write up something and we can include that here offline.
Yep. It's called a hybrid task scheduler. It's called HTGS. It's available on GitHub. We just released it less than a week ago, and we've done a lot of interesting work.
Great. So we do want to be inclusive of others who are interested in joining in with this. So thank you very much. Let's give a round of applause to all those. All right, so we're going to wrap up here with kind of talking a little bit about the design work that we started doing so far. The numbers, we've been meeting several hours a week, working through a number of things. So the purpose of this section is not to say, hey, here's our final product, but rather to do a direction check. So we don't have an API spec for you to review. We will do that and put that out in time. What we are going to do is to review some of the key things that have been characterizing some of the key directional decisions that we have. We'll go through some of those and then have a chance to poll. And if I can get Max, if you can help, or Max, if you can help when we do a show of hands later for the poll thing to be able to write that down too, if you're ready for it. Okay, so we'll just talk about the first place you want to start is with provisioning constraints. So there are a bunch up here. The nature of each one of these is believing that if we don't meet this, it will be useless. And I think we're all interested in not having useless things. So being able to be interoperable is a key thing, and working well with NPI instead of telling people, no, you need to stop using NPI, you need to use my thing, you need to use my memory allocator, or I have to own main, or I'm going to put restrictions on what kinds of things you can do. We want a couple of things that came up from guys at ANSYS, from David Fernandez, was really talking about the trade safety, right? Because it's nice to be able to have a method in anything, but it's a lot of work to prove that things are trade safe, that's implemented well. Making sure that you can get this mix of, I can do all this cool dynamic scheduling stuff, but when I need it, I need the control so that I can be able to have numerical reproducibility. So there are some of these things that might not be obvious to a casual thing that you're just trying to publish a paper on, but they're really critical for getting it right. So another thing is just sort of what we decided with this is we're trying to make the HiHAT user and common layer APIs to be very thin and very light. So all they do is essentially dispatch. And we want to make that really performant. We're actually, one of the questions we have, we'll talk about in a moment, is whether it's alignable as the APIs. Another is that, with this, you basically say, hey, here's my target, here's my other descriptors like my layout and so on, and then you'll pick the underlying implementation that people plug in. So in this layering, just to review, we have these different runtimes like those we just talked about. These are basically target agnostic, but they're informed by
what the lower layers do. And they essentially make decisions, apply transformations, call services, and so on. And in order to make the life of the many of you in the room, in the virtual room, easier, we want to have these reusable modules. So we're not trying to compete with folks that have this, we're trying to enable folks by creating an architecture for reusable modules. And then down here, to have this map and this target neutral API to a target specific application. And this is sort of ninja territory down here. And the common layer especially is the very, very thin and light, don't make any decisions, absolutely minimal overhead. So again, just a review, this is the place at the user level where you may come in with something like a logical address and need to figure out, you know, given something of this size, where do I move it? How do I move it? What is that addressing? One of the things we're looking at is essentially being able to return a handle. If you pass a handle in, you can get a handle back that says, you know, memorize. How do I do that? And that can help you with the transparency and help you to do it faster. And the lower layer is, again, a key thing that we want to have for performance. So I'm not going to go through this, but this is just suggestive of some of the different kinds of things that you could do for the computing threading. The place that you actually both work on might be OpenMP. Your tasks might have OpenMP in it, and so that you would use that. If you want to do some of the things that we just heard about for Qthreads or Argobots, you can do that. Austin just talked about one of the choices that we can use for data movement with the UCS and UCCS file. And there are a variety of different implementations that you may have here for each of these, and we're sort of trying to fill these out for each one. That's for the common layer. Similar kind of thing for the user layer. And one of the other things that, as we were thinking about this, that we want to make sure as we do the API design, we want to anticipate what are the key problems that would really affect your design and that you'd have to go do a do-over if you didn't think about it from the beginning. One of those things is if you want to be able to expand so that HiHAT, even if it's running inside a single MPI rank, would span multiple nodes, then you want those, you're going to need to use the network to be able to do that. So when it comes to data movement, you want to be able to do network. But if you're going to do something like an RDMA, that's really a split phase thing where you need to set it up and then you need to move the data. If you're going to use a relaxed memory model, you may do a bunch of writes and then sort of use a fence or use a quiet or something after that to make sure that you actually push all that stuff out. So including these things in the API is important. So we also looked at some of the challenges for how is it that we interoperate with MPI. And there's a slide on this in the backup. Essentially, we could say you can do MPI and you could use MPI for all your communication among the ranks. And we could also be the thing that you could use, HiHAT could be the thing that you use to communicate among the ranks. But then how does our implementation or whatever interoperate with MPI? MPI spec doesn't tell you how to handle that situation. And so then you're sort of at the mercy of whatever somebody did in their implementation and how they change it over time. So we're trying to tease these out and say, HiHAT is responsible for what's inside your rank or your processor, your PE. And you want to expand that, you can make the rank cover more and more of your up to a subcluster. Right? So that's a key thing that like we're sort of planting a flag, stake in the ground to be able to take that approach. And we also, with NPI, want to make sure that when data shows up from an IRC, for example, that its arrival is integrated into the rest of the dependent system. So that if you have stuff, tasks, or other things that are waiting on that arrival of that data, you can seamlessly integrate that in wherever it's coming from, you know, however, whatever across the network it is. Okay, a couple things about API design. So these are things you can stop and we can talk about these, but then we're going to do kind of a full little bit at the end to summarize things. So one of the things is how do you play in a space where you have lots of different vendors that have different levels of maturity for whatever their API? How do you know How does somebody who bellies up to the bar say, yes, that's enough for me, and I can count on being able to have whatever I need there to get functional, even if it's not tuned for the best performance. The approach we're looking to take with this is to figure out what's at the core, what's the essential things that you have to have for this to be functional. And then that's sort of, you must support that to be performant, and the goal is to be able to cover all the key targets for that. It may not have the very best performance, and it may map to, okay, you want me to do a bunch of things, so I'll do this and that, and I'll make it all happen, right? And it may be some mismatch between this and what I have as my sort of underlying implementation layer, so at least it's functional. You can then have some enhancements to this as extensions beyond that core, so some targets may support the extensions and some not. You might say, well, why not make it a free-for-all? The key thing is that we're trying to make it so that the API will capture all the semantics that we have. So that you know that when you call a given API, you know what it is supposed to do. And it's going to do extra things as much as possible. Those are captured in, and we're trying to minimize extra things that sort of aren't specified. We also know that we're all inclined to push the envelope, and so we're going to need sort of an experimental way to do things. And we're going to have a provision for being able to pass in extra metadata. It's like, okay, here's a generic API, and you can sort out what you really want to do underneath it, pass in some metadata to be able to do that. And it may be a target-specific blob. One of the things with these, though, is that there can be a nice coordination between what you do at the user layer and the common layer, and those can be matched and tuned for a given implementation. So that the implementation stuff that goes under the user layer that sort of sorts out and makes decisions and so on can know what it is that the implementation beneath the common layer is too. And you can get appropriate coordination across those. One of the key things, I've talked to more than 20 companies who say, if this only has a C++ API, I'm not interested. So making it so that you can build other things on, and for people that actually prohibit the use of C++ in their company, you can still use it for that. James, are you ready to talk about marshalling? James? Are you on mute? We can't hear you.
I think I was muted. Can you hear me now?
Yep.
Yes, I was muted. Sorry. All right, so yeah, I can talk about marshalling a bit.
You want to introduce yourself, sir?
So, sure. My name is James Beyer. I work at NVIDIA now. I spent 15 years at Cray working on OpenMP runtimes and compiler. So I have a bit of experience on that side of the world, not as much on what some of you guys have been talking about. So we're looking at marshalling, and is basically how do you move data onto the device, off the device, whatever you want to say. So we're saying it's the HiHAT client responsibility for marshalling. So the library itself isn't going to capture the data itself. The user has to, the client has to do the work of figuring out how to do the capture, build the closure. The expectation is that the runtime will be, the HiHAT runtime will be handed a closure, which is the function in the data that's going to be worked on. And then this is consistent with what compilers do today for things like OpenMP, OpenACC. It's consistent with what most people think of when they think of tasks anyway. The client can pass and do marshalling functions so that it could be a task to do the marshalling, and then another task. You can have dependencies, so you can try and stream this stuff through. What will HiHAT support? Well, we're not going to consider size. If we force the marshalling and demarshalling off onto the client, then the HiHAT interface doesn't have to worry about operand sizes and types, because it just has a blob of data that it's working with. So when it accepts a pointer and a function, and it says, okay, this is the data looks like the call function, we give you the pointer, you do what you need to do. And the one thing that's important here is to be able to build the closure. The HiHAT will need to be able to provide interfaces so that if you need to change the pointer layout, so that when you move data from one location to another, you can actually have the correct address to put into your closure. And that's all I have for that slide. All right, granularity assumptions. So one of the reasons that we push the marshalling over onto the user is it allows us to think about granularity more in computation and less about data building. So if we push the arguments in the environment and marshalling on the client, then the granularity of what a task is gets a little smaller as far as the overheads that are implicit there. What we're looking at is the code length of the task. So the function calls to set up the task, and do the dependency setup, the resolutions, the enqueuing, all that. The target selection, so inside of the runtime, what's going on to actually decide where to place the task. And that may involve figuring out where the data is, figuring out should the data be transformed, has it been transformed, so it should be run someplace else. And then starting the task up. The cost of starting a task can vary greatly depending on where it's run. If you're running it on a current NVIDIA GPU, the startup for the task there is relatively high in comparison to if you're running locally on just another thread on a CPU. So some of the things that we need to worry about for granularity is, so it takes a long time to start a task, but if we're getting a lot of speed up from that task, then the granularity of an actual task may still be worthwhile. And if we have a lot of tasks that we're getting a lot of concurrency out of it, then the overhead can be higher to start them because we have a lot of them running. So we don't have a solid number for this. What we came down to here is the 10 microsecond, 20 microsecond. If we're not talking nanoseconds, it seems to be okay. We start talking up, down there, then granularity is probably a little too small unless you have a really, really high concurrency level. Comments, questions, we can always do stuff elsewhere. Okay, and then inlining. So inlining is, everybody knows what inlining is. We do it all the time in compilers to try and specialize code, get rid of call overhead, propagate constants into your code so we can do things more efficiently. And the same thing is true of the interfaces that we're talking about here. If we allow for an inlineable header file, if there are a bunch of calls that are actually hidden underneath the call, it may be possible to bring enough information in that the compiler can restructure things. You figure, okay, I'm always going to take this path through the function. So inlining can have a major benefit, especially if your granularity of your tasks that you're actually working with are small again. So this inlining idea, although plausible, not very important for some implementations, but could be very important for other implementations. And can they work together? There's no reason they couldn't. The big thing is the inline version and the library have to agree on what they're doing. They have to underline, do the same thing, touch the same data structures. We mentioned OpenACC a little bit here because in OpenACC we did something called device type, which is kind of like inlining, and it's a way of saying, okay, this one directive applies to multiple different types of devices, and the compiler knows all about all of the devices at a given point. It doesn't have to recompile the code multiple times to see what devices. So it can specialize through the code a little bit and say, okay, I'm going to do this specific thing because I know I'm just targeting this device, or I'm going to do these special things, do data changes in unique ways for the different devices. And so, yeah, the implementation of an inline is simple enough. You can do it. And if we have our APIs well defined, the inline shouldn't be a major deal.
All right, thanks, James.
Any questions there?
So another thing that we wanted to ask here and get some open up for feedback is for these reusable building blocks that we build on top of it. We're going to provide essentially
a contract through the API and through the machine model. But what is it that we expect of people who are going to plug in something for it to get sort of the blessing to say, you know, you're officially doing everything that you need to be part of this, right? So one of the things that we've heard very strongly is that we want to be transparent about what's going on. So having some way to be to do tracing, to figure out when certain things of interest start and stop. That's something, you know, if you're going to make a scheduling decision, which ones did you make? If you're going to do a transformation, which ones did you make and what was your rationale? Why? That seemed a really stupid idea to me. You know, what was it that gave you the sense that that was a good idea, right? And to be able to report some of those things. A number of things too is to see if you say, well, it's waiting or it's running. Well, there are a lot of subtleties of, you know, have you actually bounded some resources, or are you in the process of doing that? Are you fully ready or just sort of mostly there? There are a variety of different execution speeds, and these are different kinds of things that we may wish to track and be able to support. So we would seek to have these both for the implementations that are underneath and the things that are above. And we recognize that that is going to cost you something, right? So you may want to be able to turn that off and on, but if you want to see what's going on, you should be able to. And again, we're still trying to figure out what do we really need for debugging for this. So I want to move towards wrapping up with this. So we just talked about a number of things. Essentially, we have in these areas, we have some specific proposals that those of us that have been working on this more closely for a while came up with. And we have some alternatives that weren't what we recommended. And so essentially I want to go through and first, I think you heard us talk about these, and I want to see if there are questions or comments. And after we have just a brief discussion of these, we went a few minutes left. I'd like to get a show of hands for those that are still here. And I'll do that online. But about, you know, does this look like the right direction, or do you have an argument that we should do something else? So let me just open up the floor here to see, do folks have any comments online or in the room about these particular directions? If you want to ask that clarifying question of what does this really mean, that's fine too. Networking for us, the question is, what does networking mean? Here, we want the APIs to be able to say for data movement to allow you for being able to move data across InfiniBand or something that's not just a load store access. And in particular, the part of that is that it needs to be able to support a split phase thing of, I'm going to set up a connection, I'm going to set up an ARDMA or whatever, and I'm actually going to do the per instance data transfer.
So through row one says end domain only, right? And then row two says networking. Or don't do cross domains, and why do you need networking?
Right. So we knew that we could. There's a definition later in the backup of what do we mean by a domain. So the notion here is a domain we're using loosely as a term to refer to whatever is inside a rank or a PE, and that may actually span multiple resources. So it could span CPU and multiple GPUs. It can also span a subcluster. So you may have a rank that spans a subcluster, or you may in fact be using a network between those. So HiHAT will be responsible for that portion of the hierarchy, and when it needs to move data within that, you would use whatever HiHAT uses. And when you want to communicate across ranks, you would use NPI or whatever else. So that this looks like it's a conflict, but it's not if you understand the domain to be the set of resources to which the NPI rank or PE or whatever comes. Any other questions? Yeah, now I'm going to move towards the vote. So, any questions from the bridge? Comments? Okay, so essentially the direction, just to review, we're headed here for is that we essentially want to have HiHAT cover only what's within the domain and not try to also mimic what you're doing with MPI or something else in addition. So how many people will support the proposal?
Near term?
Yes. And opposed? Okay, all hands went up for it. So that we support networking as we defined it. Supported? Opposed?
Still a little fuzzy for me, to be really honest. But like what the difference is between cross domain. Your explanation helps us, but
Okay. So suppose I have suppose I could in theory have one rank that's responsible for managing everything that happens. Suppose I have a cluster of 60 nodes. I decide to cut it in four systems. And I have 4 NPI ranks. The NPI rank is going to have really be running on one of the 4 nodes. Right? But it can be responsible for building out all the work onto those other 3 nodes. And so when it doles out the work and moves the data back and forth, it's going to use the network to be able to do that. We're going to call the 4 node subcluster to the domain with a cross switch HiHAT runs. And then they ran out of time to draw really big chunks. That's right. Okay, so again, for sports networking, yes, so against, okay, weak memory model. Anybody opposed? This proposal that we have is essentially trying to define a core set of APIs that we would, if you want to say you're conformant, you need to do that, right? We need input from the vendors and so on, and be able to do that. And then a broader set of enhancements. So for this proposal? Against? You want to speak out to that, Joe?
Oh. So,
sure, Mike.
Okay. If a standard does not have everything included, kind of fragments and splits apart, and functionality might migrate out of the core to the other places and it becomes useful, and some hardware will support just enhanced parts of the core, and it's going to become just the standard hardware because all functionality migrated to it. So there are multiple ways that this can basically undermine the effort and make it kind of split up. So that's why I would say just define what it is, define what it is not, move forward with that.
All right, thanks for volunteering to help out reviewing that and make sure we get it right. How about support for metadata for being able to do experimental stuff? Opposed? Okay, having the user responsible for marshalling and demarshalling, where they basically pass in a function and an environment with the data stuff that they pack, they get to pass in another function that goes and is responsible for demarshalling. For this? Opposed? Comment?
Like if you're going to be doing anything that is not in a shared memory space for support networking on local subclusters, then the marshalling and demarshalling is a huge burden that you're going to need some tool support to have, and if I had just completely cleanse on it, then you just raise the complexity and push a huge burden. So either don't do networking, then you have been making marshalling easier, or do networking and marshalling.
Okay, so how about this as an alternative? One of the things we've looked at is to potentially have a couple formats. So I talked about this over lunch yesterday. A couple formats that we would say marshal into this format, and then you don't need to supply any marshalling function, and just send a version number on whatever your format is, and or you can write a C++ parser that will basically take something that's a variant limited function or whatever and figure out how to do all that marshalling, stuff it into the blob, and have to squeeze out the other side. so that you can have a number of things for ease of use. But if you don't have something like that, then you have to deal with, well, how do I deal with different argument sizes, figuring out where the pointers are, doing typecasting, there are a number of other things you have to deal with in that case, is to like make your other standard. The idea is here was to go for the simplest thing we can possibly do and have that be our starting place and then let other users use things. So, can you clarify again why you think that's a bad idea?
A bad idea? No, I was saying it was a bad idea not to do, to provide no support for marshalling if you're going to do network. So, providing some support, even if it's only a limited set, saying if you conform to this, then we'll help, as opposed to not doing it all.
Okay. Thanks for volunteering how to figure out how to do it. So this is a tough one. We know there are a bunch of folks coming from the graph analytics space, for example, and a number of the things that we're doing in the deep learning space where we have really, really small tasks. And so putting my NVIDIA hat on, this is something that Stephen is spending a lot of time working on. How is it that we can add more things in the CUDA platform that we can be able to say, instead of just sort of shoving one thing down, here's a collection of things, right? And I can pre-prescribe some of the things I want to do. Looking at, Sean was pointing out here that we want to make sure we have a distinction between the latency it takes to do something and the throughput. Like, how much overhead does this take on the side of the host or whatever that's pushing stuff across? How quickly can I do that? Right? So we want to make sure that this time is low enough that we can support small granularity. We're going to push, every other vendor wants to push this as hard as we possibly can. But we like to take as an aspirational goal to be able to drive that down to 5 microseconds. We may have to revert to 10. So,
there's an expression called overhead and environment for expression of performance. I design them as half the planet. What do you mean by that?
This is granularity of work. So how small can the work or the data that needs to be done reasonably be supported within this frame? So this is not our overhead, this is the granularity of the thing that you're doing. The overhead is one order. Okay, any arguments for a number other than 5 microseconds? Okay.
I want to see you do that on a network.
Sorry?
I want to see you do it on a network.
So, and finally, we're thinking that doing inlineable headers is a nice thing, and especially for when you get to really super fine granularity, you may want to get there. Wasn't planning where it's not where we were planning to start with this. So does anybody think that being able to make a version of your headers that are inlineable is a really stupid idea? Okay. All right. So okay with not doing this at first? All right, so any other key things we've had, just sort of to survey what we've done. We had an amazing number of people that basically said, here's what I'm doing in this platform, here's what I'm doing with my runtime, here are some of the key requirements that I'd have. I think you've seen a fraction of people that across those 7 categories said high and medium is really remarkable. So we have a lot of people who figured out some things. We have a lot of work. We should all be skeptical. We should all be cautious. We should all keep feet on the ground. And I firmly believe that for this work to be successful, we really need a broad input to make sure that we don't miss stuff and we don't end up with something that's useless. I really appreciate all the time. We all really appreciate all the time and effort that you've all invested in taking the time to put together these presentations, to share your ideas, and join that effort. Are there any key things that fundamentally you think that we've missed that are really important to the API design?
You talked about heterogeneous architectures, that's in your title. You mentioned heterogeneous architectures, that's even in the title here. So being able to write tasks that will dispatch to different architectures so within the same application. And I see nothing on your list.
Okay. So we didn't, the plan in this, the design of this is that you can have a different implementation for each of the respective targets, and those can all be available in slide. You also talked about how you want us to move towards being able to care about what goes into a task, and that's essentially not what we're doing. That would leave us.
Yeah. At least be on your list and defer and listed as deferred.
Yes, it's closely related, but just how to represent tasks, that would be function players as well. Maybe something like LVM or some other representation you use represent code around. Kind of related to your stuff, but I'm with CJ where I want to register different tasks for CPU and GPU time. Well, I'm okay with that piece of it, but I need some way to represent my tasks. I sort of want to talk to the community about, how do we want to represent our tasks for actual implementations. Okay.
I think from my experience in writing code for heterogeneous, especially so-called super controls like very dense systems monitor apps. One big thing is just studying through some kind of proper abstraction how things look. We have a lot of decisions, like even right now, what you do inside of NVIDIA GPUs changes every generation, exactly how you coordinate memory and what you can do for changes. And you have to study that, because then, so you kind of want a general definition of the task model, and then you want to understand how you map that to a particular optimal scenario. Okay? And that's unbelievable. You mentioned one thing at the end I thought was good, error management.
Yes. Yeah, there's a slide later in here on resiliency, so please go ahead and look at that too. Probably last one here.
I had a question on who would be the dispatcher of these tasks. I think it's not correct. As much like would it just be a CPU sending one or just one CPU dispatch on task one, other tasks can generate new tasks, and so that there's some variations on what applications can support that dynamic tasks, not just
Yeah, okay. Right. I think we recognize that there are benefits to being able to do that in this distributed fashion as you're speaking. So, and it should be clear too that you have multiple instances of the HiHAT infrastructure and the stuff that are on top of it that are all in work. And we need to know about each other. Okay, so we should wrap up. Any final or closing comments? Great. Well, 3 hours is kind of a marathon. Appreciate you sticking through this. And I think lunch is now, and so if people want to hang out and have lunch together, for anybody that has, I'd certainly like to meet you. So please hang around. And there are a bunch of goodies that are out here too. Those are no waste. Feel free to grab some. Thank you very much. Let's do Thanks very much for coming.